ngenda tandika ekitabo kyange kiriwo. So hang on. Yes, hello, good evening. Good evening to you all. Mr. Tebusweke, we are going to start. So, as you can see what I've shared on the screen. Just kendeza. So as you can see what I've shared on the screen, that is where we are going to start from, power systems. That is what the lecturer said he would be setting. So it is a standalone topic. And what do I mean? I mean that you can study it all alone. It is individual, does not depend so much on what was previously studied. So with that case, we might be able to do what? To understand the concepts alone. So notes ezili kuneno just going kubanga unless I can copy, but again yes, Mr. Innocent, you're saying something? You raised your hand.
Yes, you can hear me.
I can hear you very well.
Have we started or have not yet started? Because
we are starting
I
right
don't know
away.
where we. Okay.
We are starting right away.
I was a bit confused whether we have started or not. This time round, I'm serious, but.
Are you going to do the test?
Hey, I'll do. Why is Kawase laughing?
I don't know. He knows why he's laughing.
I'll do the test. That's why I'm present. I'm in class.
Okay. I hope you can see my screen now. What I'm currently sharing.
Hi. It's okay. We can see.
You can see I'm sharing the screen, the notes of Ferranti effect.
Yes.
Yes. So this is the PDF that we are going to go through. It is just a matter of having 18 pages. It's having 18 pages. It is a very short thing, but it has to do with a lot of explanation. So, sorry. So Ferranti effect, first of all, I'm going to explain a little things, then we shall go to the notes and try to read through it. But I'm going to explain the basic things that you need to know about Ferranti effect before we can actually do any other thing. Is it okay? So what is Ferranti effect first and foremost? See that this Ferranti effect is an effect whereby in a transmission line, first of all, we need to know that we are going to Ferranti effect is an effect that occurs in transmission lines. It occurs in transmission lines. So which kinds of transmission lines does it occur in? It mostly occurs in long transmission lines, and it is an effect whereby, for example, if in a transmission line we have maybe it goes to a power line across this, and then we have a so-called sending end, and then we have a receiving end, a three-phase transmission line, something of the sort. So if I have this one to be my sending end, I have a voltage at the sending end which I can call Vs. and the other side I have a receiving end which has a certain voltage V receiving. So due to certain things that we might find out in a few explanations to come, we are going to find that there is a situation which occurs whereby we have the voltage at the receiving end, the voltage at receiving end being greater than voltage at sending end. So to briefly describe what the Ferranti effect is, we can say that Ferranti effect is a phenomenon which occurs in a transmission line whereby the voltage at the receiving end is greater than the voltage at the sending end. Are we together there? So initially, we all know that initially, because of certain factors that may occur during transmission, there is usually a drop across the line, and we don't expect the voltage at the other side to be bigger than the voltage at the sending end. But because of certain factors that I'm going to explain, there it reaches a certain situation in a transmission line whereby this phenomenon occurs. Now this thing is very dangerous in a transmission line because the voltage will be far greater than that which is expected, and this thing here can cause material, spoilage of machines can get burnt, devices or instruments can get burnt because of that over voltage. So generally this effect is not a good effect, and in the next steps I will be taking you through what are some of the main causes of such a phenomenon to occur. So there are things that cause a Ferranti effect to occur. First of all, if I'm to say factors or stroke conditions for Ferranti effect. So these are some of the factors, stroke the conditions for Ferranti effect to occur. The first one being that, first of all, the line has to be long. Okay, this Ferranti effect occurs in long transmission. It occurs in long transmission lines. And why does it occur only in long transmission lines? Because these long transmission lines have a certain first of all, if we are to talk about the factors that occur in a transmission line, we know that a transmission line consists of three values. That is, it has resistance, it has inductance, and it has what we call capacitance. Now, in a transmission line whereby we have resistance, inductance, and capacitance, there is always a voltage drop, and this voltage drop is always due to this resistance, this inductance, and this capacitance. But for a long transmission line, there is the effect of capacitance is far bigger than for a short transmission line. We find that for a very long transmission line, they have a bigger value of capacitance compared to the short transmission lines. So the first factor is that long transmission lines have you can call it a considerable or have a capacitance, considerable value of capacitance. Now this capacitance is the one that mainly contributes to what we call the Ferranti effect. Compared to the short lines mainly have inductance being more throughout the line. You know that for capacitance to occur, last semester when we were looking at such a thing, we used to calculate for the capacitive drop over a certain circuit. And the way we used to do this was simply by trying to draw, so we used to calculate what we call the drop over a transmission line. Just a moment. So for a transmission line, just a moment, let me drop down here. So according to the factors that they were giving us for this very main thing, they first of all talked about the line that draws a substantial quality of charging current. Now this charging current that we are talking about here is as a result of capacitance in the line. The charging current they are talking about is as a result of capacitance in the line. So briefly, I'm trying to elaborate what are some of the causes of Ferranti effect, and the main cause is due to the capacitance of the line. And we have realized that for a short transmission line, it has negligible values of capacitance compared to a long transmission line. Now, due to this factor, we have that a short transmission line having a value of capacitance. So if I'm to draw these values like this, I'll have a resistance and an inductance over the line. Yes, there is a resistance. This is a resistance, and there is an inductance over the line. And here we have a capacitance. We can concentrate it at the sending end and also concentrate it at the receiving end. Now, considering the fact that this transmission line is of this is what we call a pi equivalent of a transmission line. We call it pi equivalent because it represents all the possible values of the line in just one diagram. That is, it is in the form of a pi. So this first arm here is representing our capacitance. Remember, capacitance is always at the towers. What we used to do, there was capacitance between the lines and between the line conductor and the tower. Just to remind you from what we drew last semester, whereby we used to calculate and then we would draw capacitors here, and finally we had this. So this capacitance here occurs between there is a capacitance between the discs, okay? But now we shall consider those negligible, and we are mostly considering this capacitance between the conductor and the towers. And then we are also going to consider the capacitance between the lines. For example, if there are 3 lines like this, there is also a capacitance between them. So all this capacitance throughout the circuit has been represented at one end, that is the sending end, and at the other end being the receiving end. And over that, so this is having a value of capacitance C and C. Then here we have a resistance, we can call it a resistance R, and an inductance XL. Vectorly, it is represented by JXL. To write it in what? Vector notation. Are we together up to there? So knowing all those factors, I'm going to explain other phenomena that may result into what we call the Ferranti effect. So from that, we can further look at this diagram and explain it further. If I may represent this whole diagram furthermore like this. So this phenomenon can occur. We have two distinct scenarios in which this phenomenon can occur. There is a certain situation whereby we can choose to concentrate. Maybe these are resistances. This is a resistance, and this is an inductance, and then here we have the capacitance at the receiving end, maybe being more than that. So cutting down this circuit and eliminating what I initially had this side, I'll remain with a certain capacitance C here, and a certain resistance R here, and a certain inductance XL. So now this is the second condition for Ferranti effect 2. So this gives us the second factor to consider why Ferranti effect occurs. And the second factor is that the current flowing through this entire circuit should be dominantly capacitive. What do they mean by being dominantly capacitive? That the overall current flowing here, let me call it I, okay? The current flowing here is mostly composed of the current flowing through this capacitor, which is the IC. Suppose there is a certain load here, a certain small load, let me call it RL. So due to the fact that this capacitor here is this current flowing here in this point, the total current flowing here is mostly what? Capacitive. That means the current flowing here is almost zero. Actually, it is approximately equal to zero, because most of the current is passing through this capacitor. And what does that make our load to be? That makes our load to be very, very small. So this phenomenon of Ferranti effect occurs in circuits which are, by circuits I'm meaning transmission lines. It occurs in circuits which are lightly loaded or not loaded. You get it? So that is explaining why Ferranti effect, the main reason as to why a Ferranti effect occurs. First of all, we talked about the line being long. That is one factor. If I'm to summarize down the factors I've considered, the first one is that the line is long. It occurs in long transmission, in brackets long transmission lines. Transmission line. Then a second factor I considered is that the current flowing in that conductor, in that line, is dominantly capacitive. You get it? And then to sum all these other factors up, the main point is that the transmission line, the line is lightly loaded or not loaded at the receiving end. Are we together there? So the line is lightly loaded or not loaded at the receiving end. So this is the main cause of Ferranti effect. This, combined with the fact that the line is long, they lead to the current flowing through the circuit becomes dominantly capacitive. And now that means that the voltage at the receiving end will be greater than the voltage at the sending end, as we shall see in the calculations that are to follow from this point on. Okay? So if I'm to share with you the screen of according to what I've mentioned, and maybe to try to elaborate from the Ferranti effect, from the lecturer's notes, I'm going to just play through with you, and you will see if what I've explained to you is what is currently there now. So the first page is talking about, they're saying a long transmission line draws a substantial quality of charging current. By charging current there, they are meaning the current being dominantly capacitive. So they are saying if such a line is open circuited or very lightly loaded at the receiving end, by open circuiting there, they are referring to the circuit being not loaded. The voltage at the receiving end may become greater than the voltage at the sending end. And now they are saying this phenomenon is what is known as Ferranti effect. So the main point is to note is around this point here. They are saying if such a line, if a long transmission line is lightly loaded or at the receiving end or is open circuited, that is mean not loaded, the voltage at the receiving end may become greater than the voltage at the sending end. And that phenomenon is called the Ferranti effect. Okay? So what is Ferranti effect? Yes? Is someone commenting? So they are saying this is known as Ferranti effect and is due to the voltage drop across the line inductance being, yes, what I saying?
Yes, you asked about what is Ferranti.
Mm,
We say, as we are saying, that is an effect caused by whereby the voltage at the receiving end is greater than the voltage at the sending end.
mm,
But there are some notes which I think the lecturer had shared
mm,
because he said mainly
mm.
this effect is caused is happens in only long distance lines,
Yes,
long
exactly.
transmission lines.
Mm,
But I saw the point where it talks about medium and long transmission lines, whereby
mm.
it doesn't happen only in short lines.
Yes, yes, you're right on point. I see
Mm,
you read ahead. So yes, you're
mm.
true.
Hey.
Now the
Mm,
phenomenon does not occur only in long lines. It all occurs in both long and medium medium transmission lines, but not in short transmission lines, because short transmission lines have a negligible value of capacitance compared to long and medium transmission lines. So these long and medium transmission lines start from around hundreds of what? Hundreds of kilometers. You get it? So they start from around 100 of kilometers, and that is what we are meaning by long or medium transmission lines. From in Uganda, they might be from district to district, or from maybe Uganda to Kenya. Such lines are common. He explained further that such a scenario has ever happened in Hima. Was it in Hima, whereby the voltage, those guys lightly loaded their things, their machines. I think they shut down for maintenance works, and then they disconnected everything on their machine, on their line. Yet the line was built basically to supply them. They were the biggest consumers. So what happened is that when they switched off everything, the voltage at that side became so high. And remember, this thing was not only supplying them, but it was also being used to feed other small homes or residential areas. So the voltage became so huge that it damaged the people's property, which makes it an undesirable factor or character of the long and medium transmission lines. So for those who managed to do last week is practical. Mainly, according to me, I see that practical was mainly focused on this Ferranti effect, which is an effect of capacitance on a transmission line. So we simulated by adding capacitors to a transmission line to make it appear like a long one, and you can see that the results were wonderful. You have at the sending end, you have a voltage of 220 volts, but at the receiving end you're having 300 and something volts. So this is theoretically a phenomenon of Ferranti effect. So further on, looking on to this, to explain the notes, I hope you can see my screen. So so this Ferranti effect is as a result of both capacitance and inductance being responsible for the cause of this Ferranti, this effect, this phenomenon to occur. As we are going to see in the calculations, I will furthermore explain how it comes to occur and why it is like that. So here, when he comes into conclusion, that's where he says, therefore this phenomenon occurs in medium and long transmission line. Reason is being the capacitance is negligible in short line, but significant in medium and appreciable in long transmission lines. So they are saying that this value of capacitance, the value of capacitance C is what? Is negligible. It's negligible for short lines, but it is what? Significant for medium, and then it is appreciable. It means you cannot overlook it. Appreciable, you can appreciate it because it is of an appreciable value. So it is appreciable for long transmission lines. That's why this thing occurs in long and medium transmission lines. I hope you can see what I was writing. So knowing that as a matter of fact, next I'm going to be looking further ahead into the calculations of such a scenario, and then we see how these formulas come across. So next we shall be looking at this so-called vector diagram of a transmission line. So we shall be looking at this vector diagram and analyze how this thing comes about or is brought about. So looking at this pi equivalent diagram, the pi equivalent of this diagram, let me share what I'm writing here. So from the pi equivalent, I'll say from pi equivalent, we can have that this pi equivalent can be represented with a smaller version or simplified version. Maybe looking at case 1, when the current is only dominant and is passing through this value of capacitance C, like this. Suppose this is the value of capacitance C, here is a resistance R, and here is our inductor XL. So the voltage at this side is what I call my voltage at the sending end, can call it Vs, and the voltage at this side I can call it my voltage at the receiving end, which I can call Vr. So you find that when you consider these voltages here, suppose my circuit is not loaded at the other side, and this current flowing here is what I call my I. By virtue of equation, remember that the voltages are vector values and the currents are also vector values. Now assuming that I'm looking at the current as vectors, that means the voltage vector at this point, you can first of all say that what is going to be Vs? Vs is going to be equals to I times the drop across this, which is R, plus XL, plus voltage at the receiving end. So how do we come up with a vector equation for this diagram here? Now when this thing occurs, remember that XL is represented by a J. So when I open this bracket, I'll have my Vs being equals to IR plus J I XL. You get it? then plus voltage at the receiving end. So initially, we know that the voltage at the sending end is supposed to be greater than that at the receiving end. But how do we come up with a vector diagram for such a circuit? Suppose we are going to use the voltage at the receiving end as the reference. So using the voltage at the receiving end as the reference means that we are going to start by drawing the voltage at the receiving end in my reference diagram as my reference phasor. So suppose I'm using that as the reference phasor, the voltage is going to be this. Suppose this is my voltage at the receiving, so this is going to be my VR. Now remember that the current that is flowing there is predominantly in capacitive. I being big, I remember that I here is equals to I through the capacitor. You get it? So because it is the same current here, the current flowing the other side is 0. So this current flowing through this entire circuit is purely capacitive or dominantly capacitive. So for a capacitor, we know that it causes the current to lead by a phase angle phi, okay? Then an inductor causes a lag by a phase angle I. So capacitor leads capacitor, the current leads the voltage, but for an inductor, the current lags. You get it? So because this current is predominantly capacitive, we shall say that it is going to lead by a phase angle of 90 degrees. So it is going to lead by a phase angle of 90 degrees, and this is the current I flowing through the circuit. I can call it IC. So now when we reach at the receiving end, we are going to represent these values here. Remember, Vs is equals to the vector sum of, this is a vector sum, this is a vector, this IR is a vector because it has direction and magnitude. Then this JXL is also a vector, it has direction and magnitude. And then also this value of VR, voltage at the receiving end, is also a vector, so meaning it has also direction and magnitude. So knowing that, being a fact and true, we shall come and start representing IR. Now being IR is always in phase with the current which is flowing, so IR will face the same direction as the current which is flowing. So that will mean, yes, Mr. Innocent, have you raised your hand? Or that was from a time ago? Okay, in case you don't have anything to say, I'll proceed. So this current I through the resistance will follow the same, we will be in phase with this current flowing here. So it will come up to a certain height and it will be called my IR, because the resistance does not cause any phase shift. But now when we reach this JXL, we have a J causes us to have a phase shift of 90 degrees. And then this XL will be represented, this IXL will be represented. So that will cause me to move backwards by a certain value. Let me call it IXL. So that value there is due to the inductance. And now knowing that our voltage at the sending end is a vector sum of these two values, we shall have that this diagram here will be, after summing this is VR plus IR plus JXL. The distance from here up to the origin will give us what we call the sending end voltage VS. So this will be the VS. Someone has a question? sorry, just a moment.
I beg your pardon.
So someone was asking for me to repeat for them the vector diagram because they were confused. So I will do that again. Yes, Mr. Innocent, you were raising your arm. Your arm. Please say something.
No, 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 I'm not raising. I think it is the previous hand, but okay, let me cancel it.
Okay, let me lower it. Okay, it's fine. So someone was asking how we come up with this vector diagram. I would like to repeat a little bit. So you're seeing that our voltage here, Vs, by matter of fact, so from what we had previously here in this diagram, it is the same thing I'm going to redo. So we have a resistance here, R, which is the resistance of the line, and we have an inductance, XL. Then here we have a capacitance, C. And then we have the voltage at the sending end being V, sending, and the voltage at the receiving end being V, R. So by matter of fact, if the current flowing in this circuit, if the current flowing here is I, this means that the current flowing in these two will all go through the capacitor. The value of capacitance, the current flowing through the capacitor is IC. So that means the total current flowing in the circuit is equals to the current flowing through the capacitor. So, but remember from last time, the voltage across this point is equals to the sum of, oh my god, we've had a power blackout this side.
It soon. You just give us a minute. So continue.
So, oh my god, it is terrible.
It's okay. As long as they
Oba musobola okujja wano osimu endala nyambeko. I need more light. Oh my god, kano kagundi kankakomyewo. Anya jemu line. So kojeko screen ebiri. Ogambye you use seriously? Nga we had moved.
should I stop? Make it leave the what? Should I remove it?
Yeah, you remove it.
Not again the big another split.
It's okay. It's okay. Ampe kutala waneno katono. So let me start speaking a little bit from this side. I'm sharing my. So I hope you can see my screen. I haven't unmuted. So sorry about that, but let me continue briefly by using the notes that we are given to explain. So I was saying that the voltage at this point, you guys can log in. The voltage at this point, the voltage at the sending end is just equals to the vector. It's the sum of the current flowing through. Now for me, I've used a diagram where I've eliminated this capacitance at this point, because similarly the voltage across it is the same voltage across the the same voltage across the remaining half of the circuit. So you see that the voltage is going to be equals to the sum of the current, the total sum of voltage drops across this point. So I don't know, let me try to work out so that I can share my board on oh my god, let me see if you can see my board. Sorry, are you saying something? You can unmute and talk. Okay. So I'm going to share my screen. I hope you can see it. F9. So what I was trying to explain is this. Oh my god. Yeah, power is back. Woo. So what I was explaining is this. I hope you can see me. I hope you can see my screen. Yes, yes. So what I was trying to explain is that the voltage across this point is just this vector sum of the drops across this point. So you can see clearly that that is going to say that voltage at the sending end is equals to this current, which is a vector. That means it has direction and magnitude. So it is going to be I into the total resistance across this point, which is R plus JX. So this value XL has a certain value J, which gives it direction and magnitude. It is used to make XL a vector. So that means the current flowing through it will also become a vector. So that gives us I plus R plus J XL. This R plus J XL is just the sum of the resistances across this point. And then this will give us plus the voltage drop across the capacitor. I can call this I XC. But this I XC is equals to voltage at the receiving end, which is VR. So my voltage at sending end will be equal to I times R plus I J XL plus this IXC is representing voltage at the receiving end. Are we together there? So if we are together there, I'm going to proceed, and I hope you can see my screen clearly again. So this value here can be represented on a vector diagram. So to draw this vector diagram, I said we are going to start by using the voltage at the receiving end as the reference, because initially for us who have cheated the exam, we know that voltage at the receiving end is bigger, and we always, when we are calculating for always when we say we're calculating maybe for phase shifts and all those things considering power factor, normally it is advisable to begin with the receiving end, because the receiving end is what determines the power factor or the phase shift. So I'm going to start from the receiving end. So as you can see, I will first of all draw my voltage at the receiving end, being my reference phasor. So with everything I draw, I'll do what? I'll mark out. Remember, this is a vector, this is a vector, this is a vector, and this is a vector. All of them are vectors, so they have direction and magnitude. So representing this on a phase diagram, we shall have that if I start by drawing my voltage at the receiving end, I can grow it up a certain value, VR. So this gives me my vector for the voltage at the receiving end. Then I'll come and represent, because I put it horizontally because that is my reference. It is my starting point. We assume it is having a phase shift of 0 degrees. You get it? So we assume it is having unity power factor, in fact. So when I do that, it will align to be on 0 degrees axis. So every time you're drawing a reference, it is in the positive direction and at a 0 degrees angle. So I'll come and represent my current, and I said that my current is dominantly capacitive. When it is dominantly capacitive, that means it is like all these other values here are not existing in my circuit, but the main current is depending on the value of capacitance there. So this will cause it to be capacitive and purely capacitive, and a capacitor causes a phase shift of 90 degrees if the circuit is purely capacitive. So this phase shift will be represented with a vertical line called I. I can call it I through the capacitor IC. So if this is my value of current through the capacitor IC, then I'll come and represent. Now this VR is what I've represented here. I want now to represent my IR and the IXL. So to represent my IR, I will simply come at the end. Remember, this is just a vector sum. So where you've ended here, you can draw off the other one. You can begin by drawing this, but now this one here will confuse you because it will be a straight line along this path. So that means someone who has started by drawing this IR is far better. So I'll come and represent my IR in the diagram. So this IR, the current through the resistor, follows the same polarity like this current flowing through the device, because a resistor has no effect on power factor. For it is just a constant value, so it doesn't bring about any phase shift. So this, since it doesn't cause any phase shift, it will therefore, the vector of the voltage drop across that resistor will be in phase with the current, because for it is only depending on the current. So the current blowing here is similar to the charging current or the current through the capacitor IC. That will cause us to represent our IR in such a direction, such that this is the value of IR. Are we together there? So then, leaving alone that, I'll come and now have to represent my value. The remaining value that I have to represent is this JXL, which is a vector. But because of this J, it will cause a phase shift from the original by 90 degrees. So when it causes a phase shift of 90 degrees, that is meaning it was originally supposed to continue in this direction, but measure off 90 degrees from that, it will give us a reverse direction. And this here will cause, this value here will give us IXL, but the J has been represented by this 90 degree phase shift. So, and this therefore will lead to us having the resultant voltage, which is the supply voltage, which is a vector sum of this. When you add this, you come like this, go up, then end at this point. So the resultant there is what is going to give us our voltage at the sending end. So it comes like this and ends there. So this is going to be the voltage at the sending end. Now, it does not take a genius to know that this value here, this line here, Vs, is less than the voltage at the receiving end. You can see clearly that if I'm to make these two things parallel, and maybe to measure this from here, and I put it along this axis, it will not be greater than this point. So this vector diagram can be used to explain the phenomenon of Ferranti effect, and say therefore the voltage at the receiving end will always be greater than the voltage at the sending end. You get it? So that is how you represent this thing here by vector diagram. So if I'm to share with you what we came up with from the teacher's presentation, you can see clearly that it was representing that this is the voltage at the sending end, this is the NP is what I call my IXL, and he's representing it as the inductive reactance drop. And then NP is called, maybe MN is called the resistive drop, and OC is being called current drawn by capacitance IC. So to represent all these things on my diagram, let me share with you my presentation again. So what the lecturer is simply saying is that the value that we are getting at this point here the value that we are getting, maybe this is my reference. I may not use the same letters as he's used. Maybe let me call this A, B, and then C. So what we are seeing here as BC is our drop due to, actually it is our inductive voltage drop. And then what we are seeing here as AB is a drop due to the resistance, so that is resistive voltage drop. I'm using VD to represent voltage drop. And then what we are seeing as OA is our drop due to the capacitance, or capacitive. Does he call it a drop, or I don't know, but that is the drop due to the capacitance, and is calling it the is calling it the receiving end voltage, because that voltage across that value of the capacitance is the same voltage at the receiving end. So this is being called receiving end voltage. And maybe what I failed to represent is maybe this A, B, C, D. And if I have my OD there, is my current drawn by capacitance. Is what we call the current drawn by capacitance. The reason as why we are only referring to capacitance is because we said the circuit is predominantly capacitive. So that brings me to the next point of discussion, which is that equation that we are having there. So I don't know if you will ask us to talk about that equation. I don't know if you will ask us to talk about that equation once again, but if it does, this is what we shall be doing. So to come up with that equation, we have to consider that diagram initially the way it was. So if I have my diagram, I'll redraw it again a little bit. Sorry, just a moment. So if I have my diagram and I redraw it again, just for the sake of convenience, it is just something like this, and we have a resistance there, and then we have an inductor here. Then here we have a certain value of capacitance C, and then here we have a voltage. We have the voltage at the sending end, and here we have the voltage at the receiving end. So here we have a certain value of capacitance C. So we have a value of capacitance C, and we have a resistance R, and here we have a resistance or reactance JXL. So these two here can be summed up to form one resistor or impedance, which is R plus JXL. So knowing that the current flowing through this circuit is our I, let me call it I, and is equals to the current through the capacitor IC. So this capacitor here can also be represented by its reactance value XC. Not so? So that value can be represented by the value XC. And we know that theoretically, if we want to calculate for the value of XC is simply equals to 1 out of, it can be written 2 pi FC, but this thing here can all be represented by J omega. So this can be represented by 1 out of J omega C. And then for XL can be represented by 2 pi FL, which can be represented in terms of omega as J omega L. So whenever I'm using this, I'll for capacitance I can use J omega 1 out of J omega that. And for an inductor, I'll be using XL being equals to 2 pi F, or which is the same as J omega L. So there are two ways of calculating for this thing, and there are two common scenarios that they might be able to ask you. For example, initially I have that point. So initially I have this kind of a circuit whereby my voltage at the sending end is passing through this circuit like this, and then it is appearing through the capacitor C. So this is the first scenario, and it is considered to be called the extreme of this. It is what we call the extreme of the Ferranti effect. Here the Ferranti effect occurs extremely because all conditions are satisfied extremely. We see that the current flowing through it is predominantly capacitive, and the circuit is not loaded at the opposite end, and also the circuit is long because it has this value of capacitance C, which is unneglectable, or which cannot be neglected. Now here comes a situation whereby the lecturer draws for you a certain circuit like this, and then this time round he has drawn his circuit. Yes, I can start with my resistance R, then I take it through an inductor, and then at the other side I have a receiving end. Now I have my capacitance at the first case. My capacitance is at the sending end, and then here I have my voltage at the receiving end. So now the question arises, does Ferranti effect occur in this situation? What do you think? So the thing is that we think it doesn't, okay? And truthfully, the reason is simple, because the current flowing here, all the current, if it was supposed to be purely inductive, most of the current, if this side is open-ended, most of the current will flow through this capacitor IC. Yes, it will be predominantly, but it hasn't passed through the transmission line, so it is not appearing at the opposite end or the receiving end. So you realize that all the current will pass through here, and there will be no current flowing through this side. Realize that just the voltage across this, may be equals to this, or may not be equal, or may be even less. You see, but what is the main thing is that the Ferranti effect is not satisfied, because the current flowing through the circuit is not predominantly capacitive, and it is not passing through the transmission line. So that is the main thing. So for someone to calculate, someone looked at both of these scenarios, this case A, and this case B, and got what we call the average of the two, as I'm going to explain it in the calculation here that is to follow. So driving you further on from this point, if we are to look at the calculation for the derivation for such a formula, we shall see that so the value that is changing is the value of capacitance, the position of the capacitance. So that means our XC will be averaged, okay? So we shall consider the XC at this point and also the XC at this point, and then to combine these two circuits, because someone can see clearly that if I combine these two circuits, I'll come up with what is called my pi equivalent circuit. So the first circuit is representing this other end of the pi, and this second circuit which I've drawn is representing this opposite end of the pi circuit. So to add them together, we can add the two of them together, and we get what we call an average circuit. I don't know if you get me there. So what I was saying, just the other first circuit I drew was representing this first half of the pi, and this one is representing this opposite end of the pi. So we are going to add these two circuits together, and we are going to get the average of the two circuits. So getting the two averages of the circuits, we shall see that our XC, which is my position for XC here, is the only thing that is changing in the circuit. Therefore, I would prefer to call it, you can get the average of these two by adding them, divide them by 2. But since all of them are the same, you can simply say this this one here is going to be simply a half of the two, because here there is no Ferranti effect in this point, and at this point there is Ferranti effect. So that means the sum that will be got will just be simply a half of what we initially have. So putting that into consideration, we are going to now get the voltage at descending end. Initially, by using the other laws, suppose there is a certain drop here. There is a certain drop here. This one here, I can call it Z, the total impedance across this portion. So treating this thing as a two-port, we have a voltage at this point, Vs, and the voltage at the other side being Vr. Remember, the current is the same. So using that, the current I, which is the current flowing through this line, is equals to the current through the capacitor IC. What will that give me? That will give me that the value of this value. How can we get the value of voltage drop across this, which is Vs, okay, Vs minus voltage at the receiving end. The current is got by voltage over total resistance. So over the total resistance at this point, which is Z, is going to be equals to which is going to be equals to the current flowing through the capacitor, but the current flowing through the capacitor is represented by, you can represent it by VR over XC. Okay, it's going to be VR over XC. Initially, let me first leave out the 2, and we calculate at this point like that. Okay, so 1 over XC. Now this where it gets interesting, because 1 out of XC is a certain value we call, sorry for my online friends, 1 out of XC is a certain value we call admittance Y. You get it? Admittance is the inverse of react impedance. So I will have that my Vs minus Vr is going to be equals to over Z is going to be equals to Vr divided by, so now that will become times Y. So times the value of admittance Y. So you can take this value, but we say that this value is going to be the average. So since Y is an average value, I don't know if you can see me, the online fellows. So since Y is an average value, that means the Y we are going to use will be equals to Y over 2. Okay, so putting this into consideration, we shall have that our voltage at the descending end, which is Vs minus Vr over the Z value, is going to be equals to, what? It will be Y times Vr, but divide by 2. So I can take cross multiply by Z, and then I take the other one, the other side. So I'll have that my Vs minus Vr is going to be equals to Z Y times Vr over 2. So taking the R at the other side, I'll have that my V at descending end will be equals to Vr plus Y Z Vr over 2. Meaning that we can factorize out Vr from this side. And therefore that will give us our final equation, that Vs is going to be equals to 1 plus yz over 2 all multiplied by voltage at the receiving end. Now my derivation has eliminated out the other value that we had, which is IRL, because my value I'm using a circuit whereby they have eliminated the receiving end, the load at the receiving end. I've assumed that the load at the receiving end is 0, meaning the current flowing through it is 0. So that gives me a shorter or briefer explanation or derivation for such a circuit. So that is where we are, and that is how we come up with that formula. Now taking you back a little bit to the notes, we shall have that that equation there is what we have calculated is just simply this value you can see here, whereby it is having plus ZIR, whereby Z is the load at the receiving end. Now they have said that since IR is equals to 0, that means this value here will die out, and therefore we shall remain with a similar equation to what I've written. So we are going to also to find out how we can calculate for the voltage at the receiving end given certain values, and this is also an equation that comes up from the vector sums of these lines, as we shall see clearly from yes, this equation is what we are going to be looking at. So how to derive it is what we shall be seeing. So if I have a change of board, so from our equation that we have derived previously, I'll take you back a little bit at a certain point where we shall pick off from to calculate for such an equation. So, sorry, let me share my screen. So at this point here is where we shall pick off from, whereby we had this particular equation. This here is the equation that I'm going to go back to, because I don't want to work from this equation backwards up to here. We saw that this equation comes from this equation. Therefore, I can use this equation to do any computations. The reason I'm doing that is because I want to split so that I remain with a value of Z, Y over 2, the other side, and this value of VR can remain there, or we can even push it to this side. It is not a big problem. So I'm going to rewrite down that equation as we had seen earlier on, that the value of Vs minus VR is equals to a certain value y z over 2 times VR. So at this point here we are going to introduce the values of z and the values of y. We realize that at this point we know that the value of z is equals to r plus j omega L, and then the value of y also can be got. So initially we know that our value for z is equals to r plus j xl. So this jxl can be represented by r plus j omega L, where this L is capital L, representing the inductance of that particular inductor. And then also we shall get y, but we got that y is equals to 1 out of xc. And remember that our value for xc was equals to 1 out of j omega c. So therefore that means that the value for y is equals to what? 1 divided by 1 out of j omega c, we shall have that the j omega will come up, and therefore our y will be represented by j omega c. Now that is initial definition, but remember this is a transmission line. And remember that the values that we always have here are over a small period. So we shall need to get this by multiplying the individual resistances by the value of the length of the line. So the z total is going to be equals to this r plus j omega l multiplied by the length small l of the line, and also similarly this y is going to be equals to what we got times the length of the line. Are we together there? So using those two equations, I can substitute them in my main equation, and therefore this will lead me to such an equation whereby I will be having that my Vs minus Vr is going to be equals to the value for y was j omega c times the small l. I don't know how to differentiate it. Then all multiplied through by also this value of z, which is r plus j omega l multiplied by length, then multiplied by value of vr and divided through by a 2. Okay, so at this point there we can derive further and simplify this equation by opening the bracket. So we shall have that my source voltage Vs minus my receiving end voltage Vr is going to be equals to, now this L and this L, they will make an L squared. Okay, first of all, okay, I don't know how we should do this. Should we multiply? Remember we are multiplying this L by this L, so I can take this L to become an L squared, such that I don't have to worry by multiplying through by this again. I multiply by L, so I'll have an L squared on each and everything. So this j omega c times r will give me j omega c r L squared. Okay, then this whole thing times this will give me a negative j, because j times j will give us a negative 1. So that will give us a negative 1. Then omega times omega will be omega squared. Then we shall have a c, the value of capacitance c, then times the inductor L. This L is the L squared. Then times the value of inductor L. Then this L is the length squared. All divided through by 2 and multiplied by a certain value Vr. Now you can further open this bracket, and then you will say that Vs minus Vr is going to be equals to, I multiply through by Vr, I will have j omega c r L squared over 2 minus times this Vr here, Vr minus still omega. Now I can rearrange so that I have omega squared L squared LC. I've rearranged this CL to make it LC over 2, but multiplied also by VR. Now when you reach this point here, you are safe to say, now remember that we have a j on this number, which makes it an imaginary number, and we have a negative nothing, there is no j on this, which makes this one a real number. So this is apparent value. So when you reach here, you can only consider the real values. Therefore, by considering the real values, we shall have that. So we shall have that the value of Vs minus Vr. Now here I'm considering real parts. Of course, this Vs minus Vr, these ones here are real. I'll be equals to a negative omega squared L, this is small l squared, times L C over 2 times this value of Vr. So this leads us to that similar, almost popular equation. So this leads us to that similar or popular equation that we have seen in the calculation book. I don't know if I can get it for you. So you realize that by doing that, we are right here at the end of this point here. This equation is Vs minus Vr equals to negative Vr omega squared L squared LC over 2. So we have reached that part. For here they say they are neglecting the resistance. So for them they just simply neglected the value of the resistance. But for me, I've deferred and I've taken into consideration the real part. So it is upon you. But I think it is best to say you're neglecting the resistance, since the person who is teaching us is a doctor. So you can say neglecting resistance, but which is simply also saying taking into consideration only the real parts. So from that point there, we are going to introduce a new interesting value, because we want to come out with the values that we can simply feed into a maybe suppose we have voltage at the sending end and voltage at the receiving end. We want to come up with values that when we put them into the calculator, or we calculate, we are able to come up with a certain figure at the end of the road. So when we go back to that, so this is our equation that we had. I'm going to switch over to the next part. So if that was our equation, I'm going to rewrite it back down in just a moment. So if this was our equation, we shall know that our value from the previous equation, which was Vs minus Vr being equals to negative omega squared L squared LC over 2 times Vr. Now this one here, for those who did those resonant circuits, LC and RC resonant circuits, you know that whenever you have a combination of an inductor and a capacitor, it will read into what we call an resonance. It will have to resonate at a certain frequency. But what we are interested in is that after it has resonated and produced an electromagnetic wave, because it resonates at very high frequencies and it produces what we call an electromagnetic wave. Now this electromagnetic wave produced by this resonance will have a certain value. It will always have a certain value, which we remember all electromagnetic waves travel at the speed of light, which is what we call c being equals to the velocity of light. Now I don't know how I can differentiate this. I can call it c small l, so that you don't confuse it with my value of the capacitor. Okay, so if I use that and I call it c small l as the value of velocity of light, we know that this value of velocity of light cl is going to be given by 1 out of root L C, whereby this C is representing capacitance and this one here is representing that this L is the inductance. Are we together there? So if this L is inductance, this C is capacitance, in our equation previously, what we have here, we have an LC, and we want to eliminate that, because we shall not be always calculating for the value of inductance of the line and also for the value of the capacitance of the line. But what we want to remain with is a certain speed constant C, and these values here, omega squared, which omega we know can be calculated, and L squared, which represents the length of the line. So making LC the subject in this equation, we shall first of all square both sides. We shall know that root of LC is going to be equals to 1 out of CL, which is the velocity of light. So that means that my value for LC, when I square both sides, and I square this side, this will give me 1 out of CL but squared. Now, okay. Now the value of speed of light CL is given by 8. What is it? It is 3 exponent power 8. This is in meters per second. Now here in this, we shall not be measuring the length of the line in meters because these are very long lines. Okay, they will be measured in kilometers. So we shall use a value of CL in kilometers, and CL in kilometers we shall simply divide this by 1,000. So that will give us a subtraction of negative 3 up there. Therefore we shall have being equals to 3 exponent 8 minus 5 is 8 minus 3 is a 5. So it is 5 kilometers per second. So the value of LC that we have got is what we shall be using in our calculation. Therefore LC is going to be equals to 1 out of 3 exponent 5 but squared. And remember that when we square this, this 2 will come and multiply this 5 by 2 to give us a 10. Therefore this will give us 3 exponent 10. Okay, now the lecturer thought it wise not to use this 3 exponent 10 as it is down here, but anyway, let us first calculate here. So when I go back to my equation, my value for Vs minus Vr, putting into consideration that this is LC, yes, this is correct mathematically. So this is Vs minus Vr being equals to what we had there as negative omega squared L squared times LC network. Just a moment. What was the data? Kavudeko waneno ka disconnect. No internet. Okay, it is connected. Yes, says. Yes, Cesar, you had raised your hand. Okay, sorry about that. I had left a little bit, but I am back on air. So what I was explaining is this concept here. I was simply rewriting my equation, which was initially what I had here, Vs minus Vr being equals to negative that. So I'm adding it, but I'm going to replace the value of LC by what I had calculated, which is 1 out of 3 exponent 10. So I will have omega LC L squared. Then here I had this an LC, which I'm going to represent by 1 out of. So this will give me a 2 times my LC, which was 1 out of 3 exponent 10. You get it? Now when we were squaring here, there is something we forgot. We squared only the 10, but we didn't square the 3. So when we square the 3, this will become a 9. So this is giving me a 9 here. I hope we are together there. Exponent 10 times then the value of Vr. So the engineer was right to ask if it was mathematically correct. So the Vs minus Vr is going to give us what we are having here, which is negative omega squared L squared. Now when I open the brackets, this 9 times this 2 will give us 18 times 10 power 10 times Vr. Now what the doctor did was to take this 10 up, and therefore he came up with an equation such as Vs minus Vr being equals to negative omega squared L squared over 18 then it was times 10 power negative 10 VR. So similarly, from this point on, you can go further to bring this value of VR this side and then simplify. So when I take this VR here, I'll come up with something whereby I have that my value of Vs is going to be equals to, I can factorize it out at once. I'll have VR into 1 minus omega squared L squared times 10 power negative 10 all divided through by 18. This 18 was only on that side. So this equation here, what you're seeing here as the equation, is what we shall be using to calculate. Suppose they have given us the voltage of the line at the sending end, then maybe they have given us the length of the line, and then we want to find out what will be the voltage at the receiving end if at all the line is lightly loaded. So with that, we don't have examples in our book, but I'm going to simply share with you a simple example so that we can review and see how this is being done. So I'm going to generate a simple scenario question for us to calculate and see how it is being done, because I expect there is a calculation on this even though the man has not given us. So the only thing you need to remember is that formula, and then you also need to remember that the length is being measured in kilometers. The length we are using there, L, is measured in kilometers. So someone might be wondering how we come up with the value of omega when we are not given in the question. So I think that is what I'm going to be answering in our next scenario question. But I think you can be asked to prove this equation. So, are we together, those who are online? Sir Longo Davis, you can say hello to us as we are preparing to try and do something. I believe with that I will have finished most of the part. The other part is so theoretical that it can be read and understood, but this is the more technical part. Caroline, are we together?
Hello.
Yes, hello.
We are together, only that I joined a bit late. I delayed in the movement, a bit of jam, it caught me.
Oh,
But we are together.
okay. Okay, that we are sorry about that. But anyway, a link is going to be shared of these videos. They're always connected on YouTube and they are always accessible. So a link will be shared when this has been uploaded, possibly tonight. Just after the session, the video will be uploaded, and then we can whoever has missed out on a certain point, you can keep on following. So this is going to take me back I'm going to generate a scenario question to see how we can tackle such a thing in case we are provided with such a question. So looking at it in that form, we are going to assume, for example, I'm going to have a scenario whereby, let's say they are telling you, what is the transmission voltage? Mr. Transmission. What is the standard transmission voltage? Oh, we can use 33. Okay, so we are going to use a scenario question whereby we are going to be considering an 33 kV transmission line. Let us just consider 33, but a very long line. So suppose our line, so this is my scenario question. So suppose we are having a line running from Jinja to Fort Portal. Yes? So they are saying a transmission line, I can try to write down something maybe. So they are saying a transmission line designed to carry a steady voltage of 33 kilovolts at the sending end, sorry, so a transmission line designed to carry a steady voltage of 33 voltage at the sending end. It is a 33 volts at 50. Sorry, I forgot to add here something. A 33 kV, 50 Hz at the sending end, okay? And is, how many kilometers can we go? Let's go for 500 kilometers. Is 500, I think that is the distance between Jinja and Fort Worth. It is 300. Kampala Arua. Hey, let's use the Jinja Arua. 500 kilometers. How many hours do you use to travel that? A whole day. 8 hours. So let's say it is 80. It's 500 kilometers long. So they want us to calculate the voltage at the receiving end if the line is lightly loaded. So that is our scenario question we shall be tackling tonight. So they're saying a transmission line designed to carry a steady voltage of 30 kV 50 Hz at sending end is 500 kilometers long. They want us to calculate the voltage at the receiving end if the line is lightly loaded. So with that, let us move straight into the calculation for this question. Ready now. Okay, so with that, let us collect down the data we have been provided with. We have been provided by the voltage at the sending end being equals to 33 kilovolts. This is equals to 33,000 volts. And then they want us to calculate for the voltage at the receiving end, which is VR, is unknown. Now they have given us the length of the line is 500 kilometers, and then they have also given us the frequency, which is F is equals to 50 Hz. So when you're faced with such a scenario, first of all you need to memorize your formula. We said that our formula is such that voltage at sending end is equals to voltage at the receiving end into 1 minus omega squared L squared exponent negative 10 over 18. So you find that we have, what do we have? We have this. So we have this, we want this, we have this, we don't have omega. So how do we find omega? So to find omega, yes, so from omega is equals to 2 pi f. They have given us the frequency. That means our omega will be equals to 2 times the value of pi, which is 22 over 7, times the value of frequency, which was 50. Now calculators around here are so scarce. But maybe my online friends, if you have calculators, can give me the answer. So as we are looking for the calculator, if I'm to represent this by pi, this is 2 times the frequency, which is 50. That will give me 100 pi. So my value for omega is equals to 100 pi. So if we have that, we can represent it in the equation. We shall have that Vs is equals to Vr into, now this is 1 minus, representing the values of this. I want first of all calculate this bracket, then I will divide Vs by whatever I get in this bracket to give me the value for Vr, because it is Vr that I'm looking for. So this will be 1 into 100 pi but squared times the length. Our length was 500 kilometers squared times 10 exponent negative 10 divided by the value 18. So therefore we shall have, this is Vs minus Vs is equals to Vr into, so if I put these values into my calculator, so I'm having my value here to be 0. It is giving me 0.86. So it is 0.86 what? 629. So we can round it to 863. So the value I'm getting there is 0.863. So representing this, therefore that means my value for the receiving end, V receiving, will be equals to Vs divided by 0.863, which is equals to the value of Vs was equals to, the value of Vs was 33 kV, which is 33,000 divided by 0.863. You can calculate in kilovolts, you can calculate in thousands of volts. So we are getting a total of 38,242 volts, which can be rounded off which can, when changed to kilovolts, will become Vr being equals to 38.24 kilovolts. So clearly that, my engineers, you can see that the voltage at the receiving end is far greater than the voltage at the sending end. Remember that our voltage at sending was equals to 33 kV. So where does this extra, because for example 38 minus 33 will give us an extra of 5 kilovolts. All these kilovolts, that is an over voltage, and it will be definitely cause harm to the receiving end. So how is this thing of, now I'm not going to do any more calculations because I see time is not on our side, but we are going to discuss, of course, some of these few things. I see I'm having 11 minutes. I hope we are together at that point, but I'm going to maybe discuss with you theoretically what this what we can do to mitigate such a challenge of what, of Ferranti effect. So this Ferranti effect here, naturally, on transmission lines, is mitigated through the installation of such I don't know, there are sets of inductors installed at the receiving end of the line. Unfortunately, I'm forgetting the name of these inductors, but they draw off this excess voltage, okay, thereby balancing the system. I don't know if they are called I don't know. They are like they are like capacitor banks, but these ones are different. Are they the so-called surge arresters? Yes. So those are the surge arresters installed at the end of the transmission line, at the receiving end. Yes, they help to suck out this extra voltage and thereby help to protect the equipment of receivers, and they also improve on the voltage regulation of the entire system. Because remember, the voltage regulation, now the definition is, I can't define it theoretically, but voltage regulation is the difference between the sending end voltage and the receiving end voltage, expressed as a percentage of the receiving end voltage. So it is these surge arresters that in most cases help us to keep the voltage regulation in the desired limits, provided we have such an effect such as Ferranti effect. Now, to share with you my screen briefly, when we look from this point on, this is the point where we have reached, and the equation that we generated is simply helps us to identify that the value of sending end voltage will never be greater than the value of the receiving end voltage, simply because the value of sending end voltage Vs is equals to 1 minus something. So whenever it is 1 minus something, this is a fraction. That means whenever we have a 1 minus something, we shall always have a 0 point something. You get? So, and a 0 point something will mean that okay, let me stop using the word something and explain what I'm talking about. So from that point, when we look at that equation whereby we got that V sending end equals to V receiving end into 1 minus omega L squared times 10 exponent negative 10 divided by 18. So this whole bracket here will always give us something small. Let's say 0.x, okay? 0.x is a small value. So that means Vs is equals to 0.x times VR. That means that Vs, remember, it is the same as saying 0.x is the same as saying Vs is equals to maybe VR times over maybe a certain value x, okay, of a certain value x. I'm just assuming. So therefore this value here, the value that you get here, will always be smaller. The value of Vs you get here will always be smaller than this value, because it is similar to dividing VR. It is just a fraction of the voltage at the receiving end. Therefore, when you reach this equation, it is safe to say that Vs is going to always be less than VR, or the other way to state this is that VR is always greater than Vs. So this formula also can help you to prove the fact that Ferranti effect can exist. Okay. So sometimes they can ask you to prove the Ferranti effect graphically or by use of phasor diagrams, and that is when you represent the other diagram, which we drew first. Then when they say mathematically, by mathematical treatment, you have to derive the equation up to this point, and then you will be able to say safely that the voltage at the sending end will always be less than the voltage at the receiving end. So mitigation techniques, we have looked at installation of surge arresters. That is one of the mitigation techniques. A mitigation ways how we can, that is not in the notes, but that is we cannot vary the length of the line, because you cannot change the distance of 40 poto the origin, but maybe you can reduce the hours, the towers, the distance between the towers, the ground clearance. thereby reducing on the capacitance. So I think that is okay, but also that is a very expensive technique, because now when you increase the height of the towers, that means you're using more steel, more what. Yet the steel that you're using for the towers is not as expensive as installing one surge arrest at the receiving end. So you can, yes, do that by reducing the capacitance. How do we reduce on capacitance? Increase the cross arm space, the span of the cross arms, increase the ground clearance. Yes, but it is very expensive and might be impractical to reduce to mitigate the entire thing up to zero, because there is no way you can reduce the capacitance, but you will not eliminate it. So the only way that leaves us with the only way of stopping these power surges, or sorry, to stop this Ferranti effect when it happens, is by creating for it surge arresters to arrest that excess voltage that may arise and then dissipate it to the ground. So with that, other things that were to be looked at include this thing of the power factor management, power factor and the voltage regulation. So this next point is all about voltage regulation and efficiency. But before we go to that, maybe briefly I can explain to you what voltage regulation is and what efficiency is, and maybe we shall see there's something so important that I see I should talk about, which is to do with percentage voltage regulation, because it is also a derivation. Let me first ask you something. Are you fine to go an extra of 20 minutes?
We are very fine. Can you continue?
Okay, so I'm just going to borrow 20 minutes to explain something briefly. For voltage regulation, you will simply go through, but there is something I wanted to explain that if I don't explain now, I may never get time again to explain. So this thing here is what we call the percentage voltage regulation. So there is something what we call the percentage voltage regulation. Sorry. So percentage voltage regulation. So this percentage voltage regulation, how can it be calculated? This voltage regulation, voltage regulation is equals to the difference between the the sending end voltage and the receiving end voltage, expressed as a percentage of the receiving end voltage. Okay, so that is how we calculate for the percentage voltage regulation. It is just simply the difference between the voltages of both ends expressed as a percentage of the receiving end voltage. Now, this is going to introduce me to something that is going to wind up the entire discussion for tonight. So I'm going to go back to I may not necessarily go back to my basic, but I'm going to explain according to this. So suppose our circuit is as follows. From back, just briefly what you had reviewed, suppose our circuit is as follows, having a certain resistance R and an inductance that, and at the end we have a certain capacitance which we may not necessarily look at, but let me draw it. And we know that we want the voltage at the receiving end. This is the voltage at the receiving end, this is the voltage at the sending end. So if the value of current flowing here, and remember that we got to know that the current flowing here is a vector I, okay? So meaning it has direction and magnitude. So if this is the value of resistance R and this is the value of inductance XL at an angle J, we all know that this value here, the vector sum, for example, if we want to get the voltage drop across this point, Vs and Vr. So the value of the voltage drop across this point is going to be Vs minus Vr, and it is going to be equals to the current times the total resistance of this point. So I will call it times, it's going to be a current I, which is a vector. I can represent it with capital I, times the value of resistance across this point, which is R plus JXL. Now to represent this current I in vector form, suppose we are referring to, remember a vector, and now in this thing here, our I is going to be equals to the magnitude of the current I at an angle phi. Okay, now suppose we are referring to the receiving end. Okay, because we have said we are always going to refer from the receiving end. The angle that I'm going to consider here is going to be the angle of the receiving end. So it is going to be phi receiving. And remember that this angle, there is a phase shift of 90 degrees. Therefore, that means there is going to be a negative angle. Sorry, I'm going to consider that, for example, case 1, I'll consider for, let's say we consider for a lagging power factor at the receiving end. For lagging, PF of receiving end. So if the power factor of the receiving end is lagging, that means our phase angle phi is going to be a negative phi of the receiving end. I hope you can see that clearly. So if our phi of the receiving end is negative, that means my vector current I is going to be equals to the magnitude of it. Let me represent it by, I can use capital I or small I, but it's better to use capital I, at an angle of negative phi of the receiving end. So I'm working for the case whereby the receiving end is at a lagging power factor. So substituting for these two equations, remember whenever we are given this, for example, if we are given any vector I at an angle, okay, remember that if we have any vector value z at an angle theta, is going to be represented by z into cos theta plus j sin theta. The value of this is dependent of the angle of at that point. Yes, it is respective to the angle at that point. So if I have my I there, my vector for I will be represented by I, of course. Now this is going to be phi receiving. My online friends, you're not reminding me. So it is going to be I at an angle. It is going to be cos receiving, phi receiving. Now it is going to be minus because this phase angle is negative. So it will be minus j sin phi r. I'm doing this because he asked us to prove a certain thing in his assignment. And definitely this thing here might have to appear in his test if he is to set about these things, of course. Definitely this has to appear somewhere because he told us to prove it. So after knowing that this is this, I can substitute in this equation. So my V, now substituting into the equation, voltage at the sending end, Vs, minus voltage at the receiving end, is going to be equals to, now my I am going to represent it by capital I into cos phi receiving minus j sin phi receiving, but it is multiplied by the value of resistance plus the value j times XL. So what is simply left here is multiplying through Therefore, I'll come up with that my value for Vs minus Vr is going to be equals to I times this times that, which is IR cos phi receiving. I times this will give me plus J I XL cos phi receiving, of course. Now I'm going to also multiply I times this times that will give me a negative J I R sin phi R. Then I times this times that. First of all, I have a negative. Then I have J times J, which is going to give me a positive. Oh, J times J is a negative, so negative times negative is a positive. Then I'll have this I and this value for XL times sin phi R. So when you reach here, you only consider the positives or the real parts. So when I consider the real parts, I'll have that my Vs, we are almost there. So I'll have that my Vs minus V receiving is going to be equals to the real part of this is this first one here, which is IR cos phi receiving. Then this is imaginary, this is imaginary, this is real. So it will plus I XL sin phi R. Then to get voltage regulation, this is similar to what we had the other side. Now to get voltage regulation is this thing just divided through by VR. So when I reach here, I can say dividing through by VR, I will divide this by VR and this by VR, and this will give us the power of the voltage regulation, provided that the phase angle VR voltage regulation for lagging PF at receiving. You get it? So if you're lucky and he doesn't ask you to do this, remember you always have to multiply it by 100% to get the percentage V voltage regulation. So if he doesn't ask about this, you only need to know that for lagging power factor, the sign here is positive, and for leading, the sign here is going to be negative, because for leading power factor, you will just only represent this by a positive value because the phase angle is leading, so it will be a positive phi R, and then you calculate through the entire process and you get the power factor at leading. So that is where we stand at this point, and I think that will mark the end of tonight's discussion, unless there are other questions, but I think that is all briefly. Are we together there? So at that point, we can mark the end of our discussion. Thank you, members, for attending. Anyone to say something? Oh.
It's a word of appreciation. We really appreciate for your presentation. Thank you so much.
All right, you're most welcome, Mr. Asman. Okay. Madam Caroline, I've not heard from you tonight. I don't know if you're there. Okay. With at that point, therefore, I think we can call it a night. Thank you all. So I've closed the discussion.